In this video series, I'm going to be deriving the following algorithm, which I refer to as the Holy Grail of edge-flip algorithms. Before I begin, I would like to mention two items. Number one is I'm going to be using the 4x4 supercube. It's a cube which has arrows going in the same direction as well as all the colors on all sides being the same, just as with the normal cube. The reason that we're going to be using a 4x4 supercube is simply because centers can be affected on a cube and you can't even tell that they are. For example, if we apply the Holy Grail algorithm to the 4x4 supercube, as opposed to how it appears on a normal cube, on the 4x4 supercube, it tells us that this center and this center are swapped and this one are swapped. So it's not a clean algorithm as you would think. But see, the thing is, it swapped the same color with the same color, so you couldn't even tell that they were swapped even though they were. I'm going to be using sign notation. This is a different notation than WCA notation as well as regular Rubik's notation. It's a very useful notation for expressing algorithms for any size cube using the same pattern, and it doesn't depend on the cube size but rather just on which slices are turned on the cube and the number of slices that are on the cube as well. The first thing we need to understand to construct an algorithm is what it does. It swaps two edge pieces with each other. And of course, as I mentioned before, it does do something to the centers, but besides the centers, just focusing on the edges now, it swaps two edges, leaving two edge pieces unsolved. We can swap two edge pieces with each other by first doing an interlayer quarter turn and then pairing up all the edges again and solving back the centers using either a center algorithm that we know or just going through the trouble of solving back the centers like we normally would. And the only condition we have in order to fix this single edge flip problem is after we do this quarter turn, we keep the number of interlayer quarter turns to be even from that point. We don't make it odd again, because as of right now, the cube has an odd permutation in the inner layers. What we can do to start out, since all of these single edge flip algorithms have an odd number of interlayer quarter turns, we can just start out doing one interlayer quarter turn for simplicity. From here, what we can try to do is we can just focus on solving back two edge pieces within the slice that's messed up without affecting anything else. We will not worry about solving the centers back right now, as we will handle them later. We just need to find an algorithm which we can solve back two edge pieces, and it's ideal to solve back two adjacent edge pieces like these two, and then these two edge pieces be unsolved. And the reason we want two edge pieces to be unsolved is just because of that fact I said before. These two edge pieces are unsolved. What we need to ask ourselves is, how do we swap just two out of the four edge pieces within the slice to R without affecting any other portion of the cube except for slice to R? Actually, if you have ever solved a big cube such as the 7x7 or larger, you would probably be forced to use a center algorithm on the last two centers. We can solve back most of the centers if we try hard enough, but there still may remain some center pieces which are just not solved back very easily by intuition. What we can do is resort to a simple algorithm to solve the last two centers with ease. This type of algorithm has the following form: x, y, x inverse, y inverse. On the regular 4x4 cube, it appears that only two center pieces need to be swapped. Looking at it on the 4x4 supercube, three pieces are involved in this algorithm. So what we need to do with the center commutator, if you're already familiar with this, should be nothing new. We just move that slice up to put the piece where it needs to go, move the top face over to grab the piece from the other side, and then move the top back to put the third piece in the slot where the first piece was, and then do a few moves to restore the cube. This is the algorithm in sign notation, and clearly it is a commutator because in this case x is 2r and y is equal to u prime 2l prime u. The way this is applicable to us is because we can modify the center commutator to affect 3 inner layer edges as opposed to 3 centers by just doing a simple modification. As with the center commutator, we can first let the first move be 2r, and then the second move is u prime, and then here instead of doing 2l prime, we can do r instead to involve the edge piece here. Then we can move the upper face back and do it like this. So all we've done is a slide modification of the slices turned, and we have affected a different piece group, namely the inner layer edges of the cube. Similarly, we can affect just the corners of the cube by doing another modification of the center commutator. Instead of starting out with the 2r slice on the inner layer, we can start out with the r slice on the outer layer. Now we have a way to swap any 3 types of pieces, 3 center pieces, 3 corners, or 3 edges. What we need to do is, for our case, we need to swap 3 edges within the same slice and then do a quarter turn to solve back 2 of them, and then 2 will remain out of place. This shouldn't be a new idea. If you would just imagine these edges being corners. If you just rotate the cube like this, then what we can do is we can imagine that the corners on the outside are the single piece edges that we're trying to swap on the inside, to swap 3 of them. Because if we just rotate this way, the edge and the corner have the same 2 colors this way, and the third color of the corner you can just imagine being on the inside of the cube that you can't see it anyway. So because we want to swap 3 edge pieces on the inside, we can build from the idea of how we swap 3 corners. We just do that commutator that I showed you before. From that point, we can have 2 corners swapped, disregarding the rest of the pieces in the layer that we're working on, just by doing a quarter turn. If we just move back this inner slice, clearly this corner piece and this corner piece, they're not in the correct positions, but these 2 are. Since we already know how to swap 2 corners in a concentrated layer, this one in this case, we can do the same for another layer even though it's on the inside. At first glance, it may seem difficult to swap 3 edge pieces in the inner layer slice. However, it is not that hard if we first try to just swap 3 edge pieces and then do some setup moves before them and then invert it afterwards so that all 3 are in the inner layer slice. All we have to do is apply setup moves to grab this piece and to put it either here or here, wherever it goes easiest with the fewest number of moves. So from this point, if I add the setup move R2, I have to undo it at the end, but look what happened. These 2 edge pieces are still here. However, the one affected now is back here. And all we have to do now is just do the setup move B prime to put this edge in the spot which is affected. So when we undo it, it's up there. So I add in B prime, I have to undo it here. And look, all 3 edges are in the 2R slice now. To explain how setup moves work, imagine that the corners in these locations are cycled in one direction or the other. So suppose I wish to build off of this idea, and instead of swapping these three corners, if I wanted to swap these two corners and let's say the corner down here, what I would have to do is a setup move to place that corner into the slot which is affected by the current algorithm we have, so that the affected corner piece would be down here instead of right here. So the slot affected by the original commutator never changed. It was here, but what we had to do was move a piece into that slot affected so that it is affected when we move it back. The only reason that we were able to get away with having this corner and these two corners affected instead of these three corners affected by the original algorithm was because that the setup move that we applied, and that would, in case the shortest path would be if we just turn the front face twice and then undo it after the algorithm, was because we moved this face twice to put that corner here, but left these two slots and the corner pieces that are in these two slots originally alone. So basically a setup move works like this. We have an algorithm which affects certain slots on a cube. Then we use setup moves to put alternate pieces in the slots that are affected by the algorithm. Maybe we're going to put it in some of the slots, or maybe we have setup moves to put them in all the slots. But we always have to keep in mind that the setup moves we do need to be carefully chosen so that we affect the cube in a certain way that we wish. Otherwise, we'll be producing undesired scrambling or moving of pieces in locations which we do not want them to be in. All we have to do is do a quarter turn now, in this case 2r prime, and that will solve back these two edge pieces, and it'll have these two out of place. And now look at how the centers are. The black center is moved down here, the red center was moved here, the yellow was moved here, and the orange is moved up there. So if I just erase this entire algorithm, and if I just do 2r prime, the centers are moved in the same exact locations as if I did a quarter turn. So technically, all I have done with this commutator and setup moves as well as the quarter turn is did a quarter turn and then solved back two of the four edge pieces that were first unsolved by the quarter turn. And that is the first step that we can take to attempt to make an algorithm that we need. So from this point, actually, if we didn't worry about the centers at all, we can actually make an edge flip algorithm from what we have right now. It's pretty easy because if you've seen my derivation of the standard algorithm, then you'll understand that if we rotate the cube this way, these two edge pieces are swapped oppositely. With the standard algorithm, all we had to do was add in the moves, assuming that this was the front face, we had to add in the moves 2R2 and B2. In this case, of course, it would be 2L2U2, like this. So, to recap real quick, this is the commutator, which is just a variation of the center commutator. Then we applied setup moves to that, so that the edge it was in the back and in the right slice. Then we applied quarter turn to solve back two of the four edge pieces. And now we apply the setup moves to L2U2, and then we invert at the end to have. Cool, right? This is exactly what we want to do, except for we want to do it in a crazy low number of quarter turn moves. And we also want the centers to be preserved. Preserved as in they can be swapped with the same color, but not discolored like they are now. At this point, we have 23 quarter turns to do what we did. Our goal now is to lower our move count and preserve the centers, or make a pure algorithm. So what we first can do is not worry about the centers right now. We can throw that out for later. What we first need to do right now is just try to get the same task done in fewer moves, and we can do it pretty easily just by modifying our commutator. Instead of this, which was our original commutator, all we have to do is invert the R turns here, leaving everything else the same, and we have a commutator that actually will yield a fewer move count because fewer setup moves will be required to get the third edge piece into the 2R slice. So now taking this commutator and applying it to the cube, we don't even need that R2 setup move that we originally had in the first piece. Now that edge piece is already back here just by modifying the commutator. So all we have to do now is do the setup move B prime, which is the same as the other one. We invert it at the end, applying to the cube. It's the same exact result. So if we can just copy and paste this into what we had before in this spot right here where we omitted the R2s. Because it's the same result, so if we copy and paste it, we have that same exact thing. And now it is 4 quarter turns less, just with one modification of the commutator. So we have a 19 quarter turn algorithm so far that does this, but it messes up the centers. From this point now, I'm going to switch over to try to preserve the centers. I'm no longer going to keep it like this with a single edge flip anymore. I'm going to go back with 2 edge pieces swapped, and we're not going to apply outer setup moves anymore until the very end. So what do we need to do in order to preserve more center pieces and still just swap 2 edge pieces? What we really need to be asking ourselves is, what do we need to do to solve back more pieces? Because that's exactly what we're doing here. We're taking a quarter turn, and according to the commutator I have, it's 2R prime. And what we've done so far is we've solved back the red and black edge piece and the red and yellow edge piece. So from this point, what we have to do is keep those 2 edge pieces unsolved, but solve back more centers. How do we do that? And how do we do it that we don't add any moves to it, or if any, not that many? All we need to do is modify our commutator again, so that we can apply outer block turns. Recall that with the center algorithm, if we have the following case where it just appears that these pieces need to be solved back because these, you can't tell, are actually distorted, they're just not discolored, what we would do is just solve them back in a few ways. We could, for this case, we can solve back one at a time. Or we can just solve back all 3 at the same time by doing a multi-layer slice turn. Now suppose instead we modify this multi-layer slice turn to include the outer layer slice. And this is the algorithm we're about to apply to the 6x6 cube. Now we're involving the edge pieces and the center pieces. But this is actually not what we want to do. This is not the kind of commutator we need to do what we want to do. But this was just an illustration to show that from the center algorithm, all we have to do is a modification to include the outer layer slice, and then we have something that involves both the centers and the edges. If we want to apply a commutator which swaps blocks, what we need to do is have the slice, the inner layer slice, on the opposite side of the cube as the block slice. We can separate the inner layer slices from the block turns on a cube easily by first modifying our commutator to the following. Before, the most recent commutator that we've had is this one. All we need to do is just reflecting every turn except for the inner layer turns of 2R. taking this commutator now that's adjusted and applying it to a 4x4 cube. What we can do now is convert its turns to wide turns. Obviously, we don't want to convert all of its turns to wide, because if we did, then we'd be treating this 4x4 just like a 2x2, and that doesn't get us anywhere. What we can do for a start is convert the L turns, which we separated from the inner layer, to R turns, and make them wide, because that's why we modified this commutator in the first place. This time, we have involved the same edge pieces, but now we've also involved center pieces with them. And even though you may think that messing up center pieces with the commutator is actually counterproductive, but actually it's not, because we're going to use this commutator to swap the edge pieces, and the messed up center pieces are going to be sticking to them, so that when we do the quarter turn to solve it back, we solve back the center pieces adjacent to the edge pieces that we swapped. Looking at this, we have 3 center pieces involved here, but we're going to need to have more center pieces involved. In fact, for each edge piece we need to have 2 center pieces that are also swapped with it. If I were to make this a perfect 1x3 block swapper, that would lead us to an edge flip algorithm, but that is a different type, because that is like the standard algorithm or common algorithms that you know already. They swap the 3 individual edge pieces and that amount of centers, and then you do setup moves to make it into a pure algorithm. But clearly, as I've said, that we don't have enough center pieces messed up by the commutator to qualify to make a brief algorithm.